Welcome. This is Hiren. In this video, I will show you how to solve for Prelab 2 of Electric Circuits Lab course EE251. Okay, so let me bring up the lab first. This is Lab 2, titled Nodal Analysis. The objective is to determine the voltage across elements, the voltage at nodes with reference to ground, and also to determine the voltages at nodes with reference to other nodes in the circuit. So let's look at the background first. A little bit of background and theory is always included in every lab, and that does also include equations that would guide you into solving the pre-labs problems. So, voltage is nothing but the difference in electric potential between any 2 points in a circuit. Now, typically, when we talk about voltages at a particular nodes in a circuit, if a specific reference point is not mentioned, then we always assume it to be ground. And ground, of course, is at 0 volts electric potential. Okay. Now, voltage, unlike current, does not flow. Okay. Current flows through a circuit or a conductor, but voltage does not flow. Voltage is the difference in potential between 2 points. The difference between the potential is what would make the current flow through a circuit. So let's look at the pre-lab questions. Okay, there are 6 questions in all. Two different circuits. Well, actually 3 different circuits. The first circuit here, you can see, is a 12-volt source connected to 3 different resistors, 3 ohms, 4 ohms, and 5 ohms. And they are all in series. So let me switch over to the notes. Okay. And in the notes, what I've done is I have the original circuit here on the left. Right. The original circuit here on the left, and then I've redrawn that circuit here on the right. Now, redrawing the schematic does not mean that I'm actually changing the circuit. Okay, I'm just redrawing it in a way that would make sense to me, and also it would make sense hopefully to you. So as we can see, all 3 resistors are connected by 1 node each, and if there is a connection between 2 components at a node, we say that they are in series. And so that's the case here. We can see that the voltage source and the 3 ohm resistor is connected at node A, and then 3 ohms is connected at node B with 4 ohms, and then 5 ohms is connected with the voltage source at C. So all 3 resistors and the voltage source are in series with each other. Okay, and if they are in series with each other, then from series connection notes, we know that the current is the same. Now, one word about current direction. Obviously, when we first begin circuit analysis, we have no idea of which direction the current is going or the voltage polarity across the components, but we always assign currents using certain logic and certain laws. So for a voltage source, current always goes from minus to plus, meaning in this direction right here. And since it's going in that direction and there's only one pathway for the current to flow through, it has to make its way clockwise in that circuit. Okay. Now, what you're going to do is you need to calculate Req first, and then you apply Ohm's law to calculate the total current I that is flowing in the circuit. So you calculate Req, then you apply Ohm's law and calculate I. Once you're done with that, you calculate resistor voltages by again applying Ohm's law. Keep in mind, resistor voltages do not change because of where the ground is, right? The ground is simply connecting a certain point in a circuit to 0 volts. That does not affect the resistors itself. So if you set aside ground for a minute and then you calculate the total Req and calculate the current, the resistor voltages, the values that you obtain, will remain constant once you include ground in your circuit. That does not change. Ground is just the reference point. Think of it as a baseline with which to see and measure all other node voltages. Okay, so you calculate the resistor voltages. Each resistor voltage is going to give you the voltage between two nodes in a circuit. So think about it for a minute. Each resistor is connected between two terminals, right? And so when you find the resistor voltage, what you're doing is you're calculating the voltage that appears at either end of that resistor. Meaning if you measure the voltage at one end of a resistor with respect to its other end, that is the resistor voltage. Now, depending on the flow of the current, you should be able to determine the polarity of the voltage that appears in that resistor. Okay. And then from that point on, we can see that ground is connected at D right here. Now, typically in a circuit, ground would be connected to the negative end of a power supply, but that is not always the case. So in this circuit, the ground is not connected to node C, it is connected to node D. But again, importantly, the resistor voltages do not change. You simply consider D as 0 volts and calculate everything else based off of that. Now, for instance, if you're trying to measure VA, well, VA means you're trying to measure the voltage at node A with your reference point at ground, right there. VB similarly means calculating from B to D, and VC means from C to D. Think of it this way. If you were performing this experiment in a lab and you asked to measure VA, what you're doing is you're connecting the positive lead of your multimeter to A and the negative lead of the DMM or the digital multimeter to ground. And that is how you're going to run your measurement. So think of it that way. So VB is exactly the same way, and then VC would also be exactly the same way. Okay, VC would also be exactly the same way. Now, problem number 2 asks you to solve the same circuit, but the 12-volt source is now flipped. The 12-volt source is now flipped. Okay. Nothing else has changed. Ground is still the same, connected to node D. You have 3 resistors in the circuit. And so going back to the point that I made earlier, it doesn't matter where ground is, you calculate the resistor voltages, and then you calculate the node voltages from that. Okay. Problem number 3. Problem number 3 is the second circuit. So if you look at the second circuit right here, you have 4 resistors, and those 4 resistors are connected to a 20-volt source. Okay, 20-volt source. Now, the way you would want to begin solving this is right here. We again mark out the current direction. So I've already done that for you. Current goes from minus to plus in a source, so it's going up. There's only one pathway for the current to flow through. And it's actually coming from the top into the circuit right here via node A. If you take a look at the 4 ohms and the 8 ohm resistors, we can see that they're connected at a single node B, and the 9 and 3 ohm resistor is connected at the single node C. So when you have that, we can say that the 4 and 8 ohm resistors are in series, and the 9 and 3 ohm resistors are also in series. If they're in series, they share the exact same current. And as I've noted in my diagram right here, current I comes from the top and splits into 2, I1 and I2. Now you can call it IX, IY, IA, IB, does not really matter. The point is that the current coming from the top from the voltage supply splits into 2. It makes its way through the left branch, makes its way to the right branch, and then combines back into I at the bottom, node D. D is the node that is connected to ground. It is also connected to the negative end of the power supply. So in this case, we do not have to worry about anything. The negative end of the power supply is held at 0 volts potential. You can solve this in multiple ways. The questions being asked is to determine the voltages of VA, VB, VC, and VD. Now, we already said D is connected to ground. So you already have the answer for VD. Then you're asked to find voltage at A. Now again, think about what that means. One hint is look at the two terminals of the 20-volt power supply. See where they are connected. And that would give you the answer for VA. VB and VC, you can solve using either voltage division. Well, you would first find resistor voltages. So let me note that. You calculate the resistor voltages. And you can calculate the resistor voltages by applying voltage division, or you calculate I1 and I2 and apply Ohm's law. You can calculate I1 and I2 because the voltage source is being connected directly to all four resistors. Or a third method is to combine everything into one single resistance, combine it into Req, and then solve for the total current I. Either ways, all three of them should give you the right answer. Once you have the resistor voltages, all you have to do is calculate the node voltages based off of that. Okay. Problem number 4 is similar to circuit number 2. The only difference is you now have an additional 9 ohm resistor in that circuit. So this is our third and final circuit. You have a 9 ohm resistor connected there. And you're asked to find the node voltages for VA, VB, VC, and VD. And there's some additional questions, but once you have the node voltages, you should be able to answer the rest of the questions. So again, process will be very similar. You can calculate the resistor voltages first. Calculate resistor voltages first by either applying voltage division, or you calculate I1 and I2, or you combine it to Req and solve for the total current I flowing through the circuit. Once you have the resistor voltages, meaning all 5 resistor voltages, you can calculate the node voltages from that point on. Okay. Problem number 5. In problem number 5, what we are asking you to do is to show that the voltages between nodes A and D, the voltage between nodes A and D is the same regardless of the path you take between the two nodes. So let me explain the question. Okay, let me explain the question. It's asking you to determine VAD by taking 3 different pathways. So if we look at AD, A is right here, D is right here at the bottom. We're asking you to calculate the voltage between A and D, meaning measure at A with reference to D. Now, it asks you to take at least 3 pathways, but the thing is, there are only 3 pathways here. So it's not as if you can take more outside of the 3 big pathways. If we start at A, I can take this pathway and go to D. I can take this pathway and go to D, or I can take this pathway and go to D. And that's what the question is asking you. So what you're going to do is you take all 3 of these pathways and you apply KVL, or basically add up the voltages along that path and equate them all to VAD. Okay, you find the value for VAD for each one of these pathways, and you will find, or you will discover, that all of them have the same value, thus answering your question. Okay, all you're doing is you're adding up the voltages along that path and you equate them to VAD. Question number 6 basically asks you, what happens if you place a short between nodes B and C? Okay, nodes B and C. So if you connect a short between nodes B and C, this is what you get. There is now a third connection between 4 and 8 ohm resistors and the 9 and 3 ohm resistors. And so they are no longer in series. However, you can see that this node is the same and this node is also the same. So the 4 and 9 ohm resistors are in parallel. And so is the case with the 8 and 3 ohms. So both of those are in parallel. And then once you reduce those parallel resistors, you will see that the 4 and the 9, the combination of 4 and 9 have a relationship with the 8 and 3. And you would be able to solve again for the resistor voltages with applying either voltage division, or you combine everything into REQ and solve for the total current I. And once you have the resistor voltages, you should be able to calculate all of the other node voltages based off of those. So there you have it. Short, brief video about solving for Prelab number 2. Let me know if you have any questions or reach out to your instructors. I will see you in the next video for Prelab 3.